presenting Securing Firefox Infrastructure.
All right. Hello, everyone. My name is Adriano Sela. This summer, I had the privilege to intern with the Firefox Operations Security team here at Mozilla, and I'd like to start my presentation by talking a little bit about what we do as a team. So officially, Firefox Operations Security protects the core services and release engineering infrastructures that Mozilla relies on to build, ship, and run Firefox. And in terms of tangible projects that we work on, we do add-on signing for Firefox. So whenever you upload an add-on, we look at the contents, we inspect them for malicious code, hidden files, things like that. And once we've vetted that they're good to go, we sign them cryptographically. We also run open source security projects such as SOPS, which is a secrets management at rest solution, IPRepD, which is an IP reputation daemon, and the OAuth ZAP project, which is run by Simon in the UK. And finally, we do fraud detection within Firefox infrastructure. So what is Firefox infrastructure? So not unlike most modern companies, we host Firefox and Firefox services in a combination of cloud providers such as AWS, Amazon Web Services, and GCP, Google Cloud Platform. And the title of this presentation is Securing Firefox Infrastructure. So I'm going to start with securing them from what? Securing the infrastructure from what? So the threats that our hosts face in cloud environments such as GCP and AWS are basically the same that anything out there on the internet will face. These are cyber criminals with potential financial or political interests. We also have botnets, which are distributed processes, basically just scanning large IP ranges for known vulnerabilities and acting upon those vulnerabilities when one is found, or letting their command and control server know that they've found a vulnerability. And in the context of this presentation, I'd also like to mention the possibility of compromised credentials or a rogue employee with malicious intent. And so what are the motivations behind these attacks? So essentially, if you can get your hands on one of our hosts, you can start mining Bitcoin, make some money. Or you can exfiltrate some data, get some, essentially if you get your hands on an EC2 host that has privilege to see a database, and you get your hands on that host, you can look at the database. And all that information is money. That's all it comes down to. And other possible motivations could be to bring down or degrade one of our services. Denial of service, there is inbound denial of service and outbound denial of service. Inbound refers to clients basically overwhelming the resources that are made available to one of our hosts. And outbound denial of service happens when one of our hosts is compromised and a process within the host basically deprives the main application from using resources. So I've talked about the possible threats and motivations behind attacks. And now we move on to detectors. How do we detect the bad guys and how do we stop them from doing bad things in our infrastructure? So we can look at things at the application level, application layer, or at the network layer. For example, there are endpoint abuse indicators for an application. If a client is making your application throw a lot of 400 class errors, then there's probably something wrong. There's also, for example, if you have a service that uses accounts and your account creation endpoint is getting incremental input. For example, someone's trying to generate an account for aaa@gmail.com and then AAB and then AAC and so on. You can tell it's an automated process and you don't want that essentially. And we can look at other features at the application level and then basically we can blacklist IPs or apply violations to IPs for a certain amount of time in a way that we won't pay attention to those IPs anymore if they are seemingly malicious. And so these three things on the left side of the slide, we do those all over the place in our infrastructure. But then there's the other side of the slide, which are cloud-specific things. For example, DNS logs. What you would find in a DNS log is what are the domains that your hosts are visiting or querying. VPC flow logs are essentially ingress-egress logs for your own private network in AWS or GCP. You would be able to see like the inbound HTTP requests from source IP, destination IP, source port, destination port, all that kind of stuff, and VPC logs. And IAM event logs essentially are logs of employees logging into your infrastructure. So Bobby at Mozilla.com logged in right now, and you would get a log from that. And you want to pay attention to these things because, for example, let's say Aviles at Mozilla.com decide to give my personal Gmail account privileges. You would want to know, right? This is not something we want our employees doing, so we have ways of knowing. So these three things on the right, you can either process yourself by querying the sources of data directly, or you can pay AWS or GCP to do threat detection and fraud detection analysis of those logs for you. AWS has a service called Guard Duty, which is the logo on the left, and GCP has a similar thing, almost identical thing, called Event Threat Detection on the right. And so my internship was all about leveraging these two services, Guard Duty in AWS and ETD in GCP. And the first step in consuming those things, those findings from these services, was to sort out how I was going to get the findings from the service to somewhere where we can consume them and process them. And the architecture is kind of symmetrical on both the AWS and GCP sides. Both have the event threat detection service, Guard Duty in AWS, and ETD in GCP. Then we have a metrics and logging service, which captures the findings and takes them somewhere. That would be CloudWatch in AWS and Stackdriver in GCP. And finally, we have some sort of stream subscription service, which we can write to and read from at will. And that's Kinesis in AWS and PubSub in GCP. And I've added this slide just to point out that the architecture I came up with is modular and can be adapted to as many AWS and GCP accounts as we want, because we don't only have one, we have many, and we obviously want to have this enabled everywhere. So you saw in the previous slide all these arrows pointing at some orange thing on the right called Beam, right? So Beam is a data processing framework. And what's nice about it is it unifies batch processing and stream processing. So I'm going to define these as shortly as I can. Batch processing means you're going to collect items for a while, and then you're going to process them as a batch. You're going to keep doing that. And then stream processing means that you're going to process each item as it comes in. And typically, you can't do both at once without writing a ton of logic. But the Beam framework abstracts both of those input options for you. The word Beam is actually a hybrid between batch and stream, Beam. And the Apache Beam SDK is written in Java, Python, and Go. We went with the Java version because it was, at the time we started writing this, the most mature SDK for the framework. And part of the framework, there's also a runner interface, which is essentially where you're going to be running your pipelines. And there are options like running a Apache Flink VM or an Apache Spark VM. You can run them directly on your machine using the direct runner. Or you can do what we do in our real infrastructure, which is run it in Google Cloud Dataflow, which is a service specifically for running Apache Beam pipelines. And this is, once again, the architecture overview diagram, but I've replaced the Beam framework with the GCP environment that the Beam framework is actually running in. You can also see that there's a slide coming out of Dataflow and going to BigQuery. This is because our pipelines generate alerts based on findings. So if there's something that's significant, something that's relevant, something that we want to know about, our pipelines generate an alert, and we then write those to BigQuery just so we can come back at them for investigation purposes and whatnot. Here's what the Apache Beam Java SDK code looks like, and this is the code for my pipeline. I know it's a lot on the screen, so just bear with me. So if you look at the bottom left square, this is the highest level function in my code. This is the pipeline, essentially. You can see it's a bunch of named transforms. You parse the input, you window the input, and then you extract guard duty findings and event threat detection findings. You generate alerts based on those independently because they obviously have different fields to look at. You combine those alerts, and then we write them somewhere. We write them to BigQuery, and we also escalate those alerts. So if there's something that somebody needs to know now, we get paged for it, or you get a Slack alert, and all these options are built into the fraud pipeline. And on the right, you can see a pipeline shape diagram, which is one of the nice things about running pipelines in GCP Dataflow, is that it builds this thing automatically for you, where you can see, you can't really see it clearly on this slide, but each of those steps has a time amount, which is the total compute amount spent in that step. So you can easily identify bottlenecks in your pipeline. You can go back and make each step faster, essentially. So what does the collected data look like? What do the alerts look like? They have interesting things like account metadata, what AWS account it came from, instance ID, like EC2 instance ID, but they also have a lot of metadata about the potential bad actor. It has information about the source ISP, the ASN, the city, and the country, and so it's very interesting to query this database. I've had a lot of fun just querying it and looking at it and seeing what happens. A lot of findings also contain multiple IPs in them. So there will be cases when you see, oh, this EC2 instance in your infrastructure is being probed by these 5 IPs from 5 different countries. And so it's interesting that you can sort of, and this is something we're planning on doing in the future, coming up with some ways of doing botnet membership prediction from this data set. And I move on to talking about a week into findings. This is all the data that I collected in a non-production dev account over the weekend. And I included this slide just to give you a sense of the volume of alerts that's generated by the Gatekeeper pipeline, which is the name of my project. You can see most of them are port probes and a lot of network connection type findings. These are kind of just the noise that's out there on the internet. If you have anything hosted on the internet, it will be port probed and it will be attempted to be brute forced. And so those are those findings. They're low severity. We don't really care about them. Right now, we're just kind of looking at them, but in the end, we will suppress alerts for these kind of findings. And what I found very interesting was that AWS flagged 111 DNS requests as high severity. And I was worried at first, but then we went and noticed that, so a DNS request type finding is essentially something like, oh, your host is talking to this known Bitcoin address or a bad IP or a known malware domain. So initially it was quite worrying, but then we went and inspected the data and we realized that it was actually all these findings were accounted for by 2 or 3 web crawlers that we run, which are meant to be talking to these bad IPs and bad domains to assess the state of the web as a whole. And so that's kind of nice for GuardDuty in terms of the reliability, that we can essentially look at all the findings that we had over a weekend and account for every single one of them. And it feels like we have a lot of visibility in our infrastructure after looking at something like this. And so my personal thoughts on AWS GuardDuty, and as you may know, I've refrained from talking too much about GCP's event threat detection because they're still in the early stages. They're in the beta. But in terms of GuardDuty, I personally love that there's no need to enable additional things. It looks at independent streams of logs. So all you have to do is go on GuardDuty in AWS, turn it on, and it will look at everything that's available to it. So far, all network connection activity correctly classified as low severity, which is what I was telling you about. We haven't seen any false positives with any high severity false positives. And it's also easy to suppress findings based on a variety of features like the target EC2 instance or the type of finding, because a lot of things we don't care about. It's relatively inexpensive. And finally, the one thing that we found was kind of bad is that some severity categorizations don't align perfectly with those of Mozilla. For example, AWS will flag a IP from Tor talking to your application as a high severity finding, but we love Tor. We don't care. And finally, here are some acknowledgements about the people who made my time at Mozilla the most amazing internship I've had. That's Aaron and AJ, my most immediate teammates who worked with me on the fraud pipeline. Hal, who's the member on my team who came to see my presentation. He's the only one in this office on my team. Julian, my manager, and the rest of the folks on my team, Miles, Greg, Simon, and Bob. Thank you very much. Thank you. And most of the stuff I did is open source, and I put some links down there so you can go and have a look if you're interested. Any questions?
So you're talking about false positives. What about false negatives? Is there some way you can test to ensure that things that you consider real threats are actually detected by AWS?
So there's not really a good way to do that, other than if we claim that our threat intelligence is better than AWS and we start running things that are supposed to trigger findings and then don't. And I have personally tested this like AWS Guard Duty by deploying a Bastion host and a host with Nmap and Hydra, and attempting to brute force the Bastion host and attempting to port scan the Bastion host. And it has effectively generated alerts every single time. But yeah. Well, thank you very much.